Hey guys, welcome back to my YouTube channel. Today's video is going to be about the CPU. So let's get right into it. To start off, what is a CPU? CPU stands for a Central Processing Unit, and the CPU is pretty much the primary component of the computer. It sits right in the middle of the motherboard, and it controls the flow of data and all the instructions of the other parts. So let's say your motherboard, your RAM, your storage. It controls the instructions and the work that it needs these other components to get done in the best way. So all the components listens to the CPU, and as it's like the leader of all the components. So right now, I'm not going to get into the actual parts of the CPU. We can get into that a little bit later. But I'm actually going to go over a little bit of the architecture that's inside the CPU. So first up, we have the actual CPU. It sits right here, CPU. And the CPU, the first thing it needs is an actual input, whether it's a click of a mouse or the typing of a keyboard, anything, but it just needs an input. So input. And this input is going to go into the CPU right here. Now the CPU, it has two main parts, a control unit and an algorithmic and logic unit. So a control unit right here, and it has an algorithmic logic unit, which for short you just write as ALU. So this control unit and the ALU, they work together to do the specific tasks, and this then the CPU then works with the actual memory. So the memory right here, the RAM. So the CPU also works with the RAM to do its tasks, how it needs to fetch the data and execute its tasks. Well, where does it get the task to do? It needs to fetch it from the RAM. So that's why it communicates with the memory. And finally, after fetching it and executing the task, it gives some sort of output. So like when you click a mouse, it means open up this tab or some sort of task, it'll execute it. And finally, at the end here, you can see that we have an output. So this simple architecture is called a von Neumann architecture, and it's most common architecture used in modern day CPUs. Okay, now let's take a better look into these two parts, the control and the algorithmic logic unit. So the control unit, what is it? Well, it's pretty much the big brain of the CPU. It interprets and executes the instructions that are got from the RAM, and it's like manages all the data flow, and it acts pretty much as the brain. While the algorithmic logic unit, it's more for mathematical parts, as you can see in the name algorithmic. It does more mathematical computations in binary and logical computations based on the data, and it acts as like the core component that executes all of these functions. So a better drawing is right here, and we can see how it's the same exact thing. It's the input, you get some inputs, the mouse click or clicking of a key, whatever, and you can see this is the actual CPU. It has a control unit and the ALU, and you can see that it communicates with this memory unit or the RAM, and it goes back and forth communicating, getting instructions, and finally it executes the task and it outputs something, outputs whatever. But you see how we first start by fetching an instruction from the RAM. You see this arrow right here shows that the CPU is fetching some information from the RAM. Now the RAM will give it some information or a task that it needs to be processed. So that's the arrow going back into the CPU. So now the CPU has a task it needs to process. It needs to decode the instruction that it got from the RAM, and it needs to output something. So let's say you click it and you need to go into some link. So that means that the task is to open the link. So it receives the task from the RAM and it executes the task. And this method, this cycle, is called a fetch, decode, and execute cycle. So first you're going to fetch the instruction from the memory. So you're fetching the instruction from the actual memory, as shown here. And then you decode the actual instruction. So the CPU is going to decode what the actual instruction it just got and what it should do. So, and it turns into binary values, which is what the ALU is for. It turns into binary values, which the computer can actually understand. And finally, it executes the instruction and produces some type of output. So once again, this is called a fetch, decode, and execute cycle. And you can see here, we have the control unit. and this is more specific what each unit does. The control unit, it decodes the instruction that it fetched from the RAM. It fetches from the RAM, the control unit decodes it. The algorithmic logic unit executes it by turning it into binary and executing it. And finally, it goes back into the RAM and stores it here, and it's just a continuous cycle. All right, so now that we have the simple CPU architecture down and what a fetch, decode, and execute cycle looks like, we can take it a little bit step further into the cycle, and we can look at something called registers, which is this main part here. All right, so let's take a quick look at this. So over here, you can see we have a RAM, some memory over here, and on this side, we have a CPU. And inside the RAM, you can see that we have an address and a value section. The address is just numbers from 0 to 1, 2, 3, 4, 5. And this is like 0, 0. These 8 zeros is the number 0. This 1, 1 is the number 1. This is the number 2, and so onwards. And then this value is some other type number of binary. And you can see here on the CPU side, we have a program counter, which is going to count the specific step that we're on, and the instruction register, which is like the actual task that we need to compute. So this all ties back into the actual cycle, the fetch, decode, and execute cycle. So the first thing that's going to happen is we're going to go to the program counter, the CPU's program counter. And it's going to say, okay, well, we're going to start from the number 0. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, which is the number 0 in binary, or step number 0. So it's kind of like step number 1, and it starts with the number 0. And so the program counter is going to go, okay, well, we're starting with step number 1, which is this 8 zeros. So let's look at our address. It's going to come here to our RAM, and it's going to come to the address value, to these addresses numbers. And it's going to look, okay, which number matches up? Well, it's going to be this address right here. Okay, good. I found the address. What am I going to do now? Well, now I need to find the actual task that is linked with this address, the value. So just to recap, the address is the specific step, 0 to 5, that's shown in the example here. And the value is a specific task. So the program counter comes to the address section, matches up with the correct counter, and it finds the task or the value, which is this right here. And it's going to bring this value all the way back here. So what steps have we just done? Well, we've got the fetching from the RAM. We got the program counter to fetch the specific value from the RAM. And now it comes to the instruction register, and it's going to write our specific instruction. It's 0, 1, 1, 0, 0, 0, 1, 1. And finally, it's going to do the actual computation. So the ALU is going to come in, and it's going to finally compute this task right here. And after this task is computed, it's decoded, and finally it's executed, which is the final two parts. Once it's executed, our step is now going to become number 2. This step is going to become number 2, and instead of 0, 0, 0, 0, 0, 0, 0, 0, it's going to increment by 1. So we're going to go to 1. This is going to turn into a 1. So it finds, now we're going to go and we're going to look for the address in our address values. And you can see that it matches up with the second number here. We take the value comes to the instruction register. The ALU computes it and it executes. And then the step increments again. So now the step will become 3 and then 4 and so onwards. So this is how specific tasks get done in the CPU. The program counter goes to the address section in the RAM. It finds a specific value. It returns the value into the instruction register. And finally, the ALU will do some computation and finally execute it. And it keeps doing the cycle over and over again. So this instruction register right here that was used to get the value and make the ALU compute the actual value and the task and finally execute it. This register is what I was talking about over here. This is what the registers are for. It's kind of like this in-between step and it all comes together to finally form this fetch, decode, and execute cycle. So now that we finished the simple architecture and the entire fetch, decode, and execute cycle, we can go over some actual components that are on the CPU. For example, these pins and what these tiny little boxes are. So we can start with what these actual boxes are. And these boxes are called cores, cores. And each core is designed to handle some specific application. For example, some window or some gaming application or stuff like that. So the number of cores is pretty much how efficiently you can open up that many applications. So let's say you have eight cores. It's each one of those cores is able to efficiently handle a different application or a different task. So one way that I like to think of it is the cores are pretty much like the neurons of the brain. There's a bunch of different cores and they all work together to perform the task, and they each have their own specific task that they need to do. Now, under cores, you have this next component, which is called threads. Threads are kind of like tiny tasks that each core has to do, that each core can handle. So let's say you have a chef or a group of chefs. The entire group of chefs working together to cook some food, that entire group is pretty much the CPU. Now, if you take one single chef is acting as a core. It has a bunch of different tasks to do. It has to cook the food, cut some stuff, fry some stuff. So the chef represents one core. It's kind of like it's one part of the CPU. Now, if you go even further into the chef has some tasks to do. Like I said, cutting the onions and frying stuff, turning on the stove. Those are all simple tasks, and those are what threads are for. So it's all like a step down pyramid of what each part inside of the cores are. So you start with the CPU, then you have cores, and then you have threads. So the more cores and threads that you have, pretty much the more efficiently your computer can handle more and more tasks. So the next component that I'm going to go over is cache. Cache is kind of like a small short-term memory. So let's take an example. Let's say you go to a library and you want to read some books. You can every single week go to the library, read some books, come back. So whenever you want to read books, you have to keep going back and forth to the library. But that takes a lot of time and it's just a waste of time. So what can you do instead? You check out books and you take them home and you put them on your desk. And this is easier so that whenever you want to read, they're right on your desk. So you can use them really quickly. You can open up your books and just immediately start reading. The problem with this is that there's not a lot of space on your desk to keep the books. So this is kind of like the idea of cache. So the cache will go to the actual memory, the RAM, and it'll fetch a little bit of data. And you can see here in these images, like the L1 cache, L2 cache, and L3 cache. These are all different types of cache, all with different like specifications. For example, L1 cache is faster, but it doesn't have as much storage as L2 cache. But anyway, so a cache will go to the main memory, the RAM, and it'll go and fetch some data. And when it does that, it'll take it and bring it to the CPU chip. And now, whenever the back here when we had the RAM and CPUs, these fetch, decode, and execute loops, when they need to fetch the instructions from the memory, it's a lot easier to store a bunch of memory in the cache so it doesn't have to keep taking long trips all the way to the RAM. So that's the idea of cache. So where do we see cache actually being used in our computer? Well, let's say you open up, for example, YouTube for the first time. So you go to youtube.com and there's a bunch of different logos and thumbnails, and you'll see a bunch of different accounts on the sides. And so all of this information is being stored in the cache. So the first time you open up the website, it's really slow, right? But now let's say all the next times you open up YouTube, right? You go to YouTube, all the previous information that's still being reused, for example, the logo and your subscribed accounts and all that, it's all already processed. So the YouTube link will load a lot faster. But of course, there's new stuff, for example, new thumbnails, which will have to be reloaded again and stored in the cache. But it still is a lot faster way. So that's how we can see cache used in our regular daily use on the computer. So a good definition that I found of cache was it's pretty much the data and instructions that are loaded before being accessed by the rest of the CPU. So taking all the previous data, storing it in the cache for later use. So So it's like a short term and not very big amount of memory, but it makes the computer run a lot faster so that it doesn't have to take long trips to the RAM or storage. So that's pretty much it for this video. There is a lot more to the CPU, central processing unit, a lot more different components to it. But this is the basics fundamentals of what the CPU is made of, like the how it runs, the fetch, decode, and execute loop, and simple architecture and basic components that are on the actual CPU. So yeah, thanks for watching. See you next time.